Hello everyone, welcome to the third section of my tutorial on data pricing from economics to data science. In this section, we'll talk about the fundamental principles of data pricing. In this section, we first review the idea of versioning, which is a fundamental framework of designing information goods and pricing them. Then, we'll review several important properties in cost models of digital and data products, including truthfulness, revenue maximization, fairness, arbitrage-free pricing, privacy preservation, and computational efficiency. Versioning. As the replication costs of information goods are very low, even approaching zero in many cases, the price of an information good tends to be very low in marketplaces too. The potential of very low prices of information goods, on the one hand, makes information goods economically appealing, and on the other hand, may also make information goods economically dangerous, as the competitors may easily enter the market. This dilemma keeps many traditional pricing strategies far away from their being effectiveness. To solve the dilemma, the core idea is linking price to value. That is, we set a price reflecting the value that a customer places on the information. Especially, the versioning strategy makes different versions to appeal to different types of customers. For example, for a piece of software, different versions have different subsets of features. Different versions of a movie may provide different image resolutions and sound effects. Essentially, versioning divides customers into subgroups so that each subgroup may regard some features highly valuable and some other features of little value. A version corresponding to the demands can be provided. There are many different ways to produce different versions of information goods. For example, delay is often a good basis. In stock market information services, an expensive version may deliver real-time codes, while a basic version delivers the same information 20 minutes later. In addition, versions may be defined by convenience, such as data can be accessed only by PDF file or by downloadable spreadsheet. They also can be defined by comprehensiveness, such that the length of historical data available, or by manipulation, such as whether users can store, duplicate, print the information. Or they can be defined by community, meaning the availability of posting and reading discussion boards. Sometimes it may even be defined by annoyance, meaning the option of no advertisement. Or there are many other factors may be considered. Most versions of information goods are created by subtracting values from the most technologically advanced and complete version. In many situations where customers may not realize the value of an information good unless they try it, even the free versions may be provided. The rationale here is that the free versions can provide opportunities to potential customers to test out. The objectives of offering free versions include building awareness, gaining follow-on sales, creating a customer network, attracting attention, and gaining competitive advantages. How many versions should be made? The number of versions of an information good may be divided by two major considerations. First, the characteristics of the information to be sold is important. An information good that can be used in many different ways opens the door to many different versions. The second important factor is the value that different customers may place on it. The versioning strategy has been investigated in pricing data products, relational datasets, and query results in specific. Relational views provide a natural and flexible technical mean to produce versions of an information source. A series of technical challenges are identified, such as arbitrage in pricing, fine-grained data pricing, pricing updates, integrated data, and competing data sources. We'll review those later in this tutorial. There are a series of important data in data pricing. There are many different ways to design and implement pricing tools and pricing models for information goods. There are a small number of data pursued by most models. How to implement those data in pricing models will be discussed in later sections. First, let's look at truthfulness. To make a market efficient, the market is preferred to be truthful. A market is truthful if every buyer is selfish and only offers the price that maximizes the buyer's true utility value. In other words, in a truthful market, no buyer pays more than sufficient to purchase a product. Here, different buyers may have different utility values on the same product. Truthfulness can facilitate a wide spectrum of pricing mechanisms, such as many kinds of auctions. Auctions of products will be discussed in the next section. The second principle is revenue maximization. Pricing models can optimize different objectives, such as lowest cost, highest profit, and largest sales. The objective of maximizing revenue is often of specific interest in designing pricing strategies. The rationale is that for a business to be successful long-term, a more immediate and important requirement is to win over as many customers as possible. For traditional physical products, it is often assumed that the marginal cost goes up after a certain number of units are manufactured, and thus the profit can be maximized if the output level is set so that the marginal revenue is equal to the marginal cost, and the revenue can be maximized if the marginal revenue becomes zero. However, given that the replication costs of information goods are very low, revenue maximization and profit maximization for information products become quite different from the physical products. Fairness. Essentially, a market is fair if each seller gets the fair share of the revenue in collection. In his seminal article, Shepard lays out the fundamental requirements of fairness in markets. Suppose there are K sellers cooperatively participate in a transaction that leads to a payment of V. There are four basic requirements. The first requirement is balance, meaning the sum of the payment to each seller should be equal to V. That is, the payment is fully distributed to all sellers. The second requirement is symmetric. That means for a set of sellers S and two additional sellers S and S prime who are not in S, if adding S to the big S or adding the S prime to the big S produce the same payment, then S and S prime should receive the same payment. In other words, the same contribution to utility should be paid the same. The third requirement is zero element. For a set of sellers S and an additional seller S prime, if this S union this S, small s, and the big S produce the same payment, then this small s should receive a payment of 0. In other words, if one member does not make any contributions, the member should not receive any payment. The last requirement is additivity. If the goods can be used for two tasks, T1 and T2, with payments V1 and V2 respectively, then the payment to complete both tasks T1 plus T2 should be V1 plus V2. In the above well-celebrated Shapley fairness, the Shapley value is the unique allocation of payment that satisfies all the requirements. The formula of the Shapley value is given at the top of the slide. Here, U is the utility function, D is the complete set of sellers, the big S is a subset of D, is a set of seller, and the small s is a seller. As you can see in this formula, essentially, the Shapley value of this small s is the expectation that in all possible subsets big S in this D, what's the contribution of S in utility? So equivalently, this equation can be rewritten in the following way, which is pi is the permutation of all sellers and pi is the set of sellers preceding S in pi. There are some studies observed that as the replication costs of information goods are very low, the marginal costs of productions are close to 0. A seller can produce more units of the same information good to obtain a large Shapley value and thus a large portion of the payment unjustified in business. This is a challenge in designing fair marketplace for information goods. Arbitrage-free pricing. Arbitrage is the activities that take advantage of price differences between two or more markets of channels. For example, a user wants to purchase the access to an article whose list price is $35. Suppose that the journal publishing the article has a monthly subscription rate of $25. Then, the user can conduct arbitrage to subscribe to the journal for only 1 month and obtain the article at a price cheaper than the listed price. Arbitrage is often undesirable in pricing models. At least it should be able to check whether a pricing model is arbitrage-free. However, arbitrage may sneak in pricing models that are not thoroughly designed. For example, suppose a data service provider sells query results with prices based on variance. A variance of 10 for $5 each query result, and a variance of 1 for $100 each query result. Each answer is produced independently. A customer wants to obtain an answer of variance of 1 can indeed purchase the query 10 times and compute their average. Due to the independent noise in perturbation, the aggregated average has variance 1, and thus the customer saves $50. Privacy preservation. Privacy is becoming a more and more serious concern about information goods. In general, privacy is the ability of an individual or a group to keep themselves or the information about themselves hidden from being identified or approached by other people. Privacy is highly related to information and information exchange, which are information goods about. As explained in Section 2, due to the low checking cost of information goods, it is easier to collect data about user privacy. Whether privacy should be treated as goods and how privacy is priced will be discussed later. It is highly desirable to preserve privacy in marketplaces of information goods. In general, transactions in a marketplace may disclose privacy of various parties in many different ways. First, privacy of buyers is highly vulnerable. Their identities, the location and time of purchases, specific products purchased, the purchase price, and total amount may reflect their privacy. It has been reported from time to time that e-commerce providers leak customer information by mistakes, such as an accident reported recently. Second, privacy of providers of information goods may also be disclosed. For example, medical treatment information in hospitals is highly valuable, for example, for pharmacy medical equipment companies. Imagine that hospitals can collect and anonymize medical treatment data properly and provide the corresponding data products in marketplaces so that individual patients cannot be identified. Buyers, however, may be able to infer from the data the successful rates of a specific treatment in a hospital, which may be regarded as the privacy of the hospital. Last, transactions in marketplaces may also disclose privacy of a third party involved. For example, an AI technology company may provide a machine learning model building services to data product buyers. However, machine learning models may be stolen, which are regarded the privacy of the AI technology company. To protect privacy in marketplaces of information goods, various directions are being explored, such as hiding the information about what, when, and how much a buyer purchases, building decentralized and trustworthy privacy preservation data marketplace, investigating the trade-off between payments and accuracy when privacy presents, and aggregating non-verifiable information from a privacy-sensitive population. There are many studies on privacy preserving in information goods. We refer interested readers to consult the rich body of surveys and others. In this tutorial, we will not discuss further details about privacy preservation techniques, since privacy preservation techniques are far beyond the scope and capacity of this survey. Last, computational efficiency. As many information goods may be sold to a huge number of potential buyers, a pricing model has to match goods and sellers and buyers with an appropriate price. Computing prices efficiently with respect to a large number of goods and a large number of buyers presents technical challenges. For example, one reasonable expectation is that a marketplace is polynomial. That is, the complexity of computing prices has to be polynomial with respect to the number of sellers and cannot grow with respect to the number of goods or buyers when prices are updated. When auctions are used in determining prices, auction efficiency, which is the time needed to process bids, is required to be fast. In summary, versioning is a common mechanism in designing and pricing information goods, so that prices of different versions can be linked to values placed by various customer groups. There are a series of important requirements on pricing information goods, including truthfulness, revenue maximization, fairness, arbitrage-free pricing, privacy preservation, and computational efficiency. Those requirements pose technical challenges to pricing models. This wraps up the third section of the tutorial on data pricing from economics to data science. Thank you.